The ultimate question: what came before the Big Bang? Have you ever looked up at the night sky and wondered where it all came from? The vastness of space can make us feel small and curious. How did this vast universe filled with billions of stars and galaxies come into existence? What sparked the creation of everything we see? This is perhaps the biggest question humans have ever asked. What existed before the universe? What was the state of reality before time and space began? The quest to answer this question has captivated scientists, philosophers, and dreamers for centuries. Each generation has pondered the origins of our cosmos. For a long time, the answers seemed lost in the mists of time. Ancient texts and early observations provided little clarity. However, with the advent of modern science, we have begun to unravel some of the universe's deepest secrets. Advanced technology has opened new windows into the cosmos. One of the most important discoveries in cosmology is the Big Bang theory, which suggests that our universe began from a state of extreme density and temperature about 13.8 billion years ago. This theory has provided a framework for understanding the early universe. The Big Bang theory has revolutionized our understanding of the cosmos. It has reshaped our view of the universe's origins and its ongoing expansion. It explains a wide range of observations from the expansion of the universe to the abundance of light elements. These observations have been crucial in supporting the Big Bang model. But the Big Bang theory doesn't answer all our questions. It leaves us with many mysteries still to solve. In fact, it raises some of the most profound and perplexing questions of all. Questions that challenge our understanding of physics and reality. What was there before the Big Bang? Was there a different kind of existence or a different set of physical laws? And what caused this cataclysmic event that brought our universe into existence? Was it a random occurrence or part of a larger cosmic cycle? Join me on a journey to the very edge of our understanding. Let's explore the frontiers of science and the limits of human knowledge. Together, we'll explore some of the most mind-bending ideas in modern science. Concepts that push the boundaries of what we know. We'll delve into the mysteries of the Big Bang, the nature of time and space, and the possibility of other universes beyond our own. Could there be multiple realities existing simultaneously? Get ready to have your mind blown. The journey ahead is filled with wonder and discovery. The Big Bang, our universe's explosive beginning. Imagine a time when the universe was not a vast expanse of stars and galaxies, but an incredibly hot, dense point smaller than an atom. This is the picture the Big Bang theory paints, a universe bursting forth from a state of unimaginable density and temperature. It's a concept that boggles the mind but is supported by a wealth of scientific evidence. The Big Bang theory suggests that around 13.8 billion years ago, space and time as we know them came into existence. This wasn't an explosion in the traditional sense, like a bomb going off in a pre-existing space. Instead, it was the expansion of space itself, stretching and cooling, carrying with it the seeds of everything we see today. One of the key pieces of evidence supporting the Big Bang is the observation that the universe is expanding. Distant galaxies are moving away from us, and the farther away they are, the faster they seem to be receding. This observation, known as Hubble's law, suggests that the universe was once much smaller and denser. Another crucial piece of evidence is the cosmic microwave background radiation. This faint afterglow of the Big Bang permeates all of space and provides a snapshot of the universe as it was just 380,000 years after the Big Bang. By studying this radiation, scientists have been able to learn a great deal about the early universe. Time. Did it begin with the Big Bang? The Big Bang theory presents us with a mind-boggling concept, the beginning of time itself. If the universe began from a point of infinite density, does that mean time also began at that point? Did time, as we understand it, simply not exist before the Big Bang? This is a question that has puzzled physicists and philosophers for decades. Our everyday experience tells us that time is a constant and ever-flowing river that carries us from the past to the future. But the laws of physics, particularly Einstein's theory of general relativity, suggest that time is not absolute but rather a part of the fabric of the universe, intimately connected to space. According to general relativity, gravity warps space-time. Massive objects like stars and galaxies create distortions in the fabric of space-time, causing time to slow down in their vicinity. This effect, known as time dilation, has been experimentally verified and has profound implications for our understanding of the universe. If gravity can warp time, then it stands to reason that the extreme gravity of the early universe, near the singularity of the Big Bang, could have had an even more dramatic effect on time. Some physicists believe that time as we know it may have indeed begun at the Big Bang, while others speculate that time may have existed in some different form before the Big Bang. Section 4. The Singularity, a Cosmic Puzzle. At the heart of the Big Bang theory lies a concept that both fascinates and frustrates scientists: the singularity. This point of infinite density and temperature, where the laws of physics as we know them break down, marks the very beginning of our universe, but it also represents a fundamental challenge to our understanding of the cosmos. The singularity is a point where our current theories of physics simply cannot describe what was happening. As we approach the singularity in our models, the density, temperature, and curvature of space-time become infinite, creating a situation that defies our current mathematical and conceptual tools. Imagine trying to squeeze all the matter and energy in the entire universe into a space smaller than an atom. That's essentially what the singularity represents, and it creates a dilemma for physicists. Our current theories, such as general relativity and quantum mechanics, work incredibly well in describing the universe on large and small scales, but they fail to provide a complete picture of what happens at the singularity. This breakdown of our understanding suggests that we need a new theory of physics, one that can unify gravity and quantum mechanics into a single, coherent framework. This theory, often referred to as a theory of quantum gravity, would hopefully allow us to peer beyond the singularity and gain a deeper understanding of the universe's origins. Section 5. Beyond our universe. Exploring the multiverse. The Big Bang theory describes the origin of our universe, but what if our universe isn't the only one? What if the Big Bang was just one of many such events, each giving birth to a different universe? What if there are other universes out there, each with its own unique laws of physics, its own history, and perhaps even its own forms of life? Imagine a universe where gravity is stronger, or where time flows differently. This is the mind-boggling concept of the multiverse, the idea that our universe is just one of many universes existing in a vast, interconnected cosmic web. Each universe could be a bubble in this grand cosmic foam. The multiverse hypothesis arises from several different areas of theoretical physics, including cosmology, string theory, and quantum mechanics. These fields, though distinct, converge on the possibility of multiple universes. Each of these fields offers tantalizing hints that our universe may not be alone. The evidence is subtle, but it builds a compelling case. One compelling piece of evidence comes from cosmology. Observations of the cosmic microwave background radiation suggest anomalies that could be explained by interactions with other universes. Inflationary cosmology, an extension of the Big Bang theory, suggests that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. This rapid expansion could have created multiple regions of space-time. This rapid expansion could have created bubbles in space-time, each of which could have given rise to a separate universe. These bubbles could be floating in a higher dimensional space. String theory, another leading candidate for a theory of everything, also predicts the existence of extra-spatial dimensions beyond the three we experience in our everyday lives. These dimensions could be compactified or hidden from our perception. These extra dimensions could potentially harbor other universes, hidden from our view, but nonetheless real. They might be just a fraction of a millimeter away, yet completely inaccessible to us. The multiverse hypothesis, while still highly speculative, is a captivating idea that has profound implications for our understanding of the cosmos. It challenges our notions of reality and our place within it. If our universe is just one of many, it raises new questions about the nature of reality, the uniqueness of our own existence, and the possibility of one day interacting with these other universes. Could we ever travel to these other realms or communicate with their inhabitants? The possibilities are as endless as the multiverse itself. Section 6. The Cyclical Universe. A never-ending story? What if the Big Bang wasn't the beginning of everything, but rather just one chapter in an endless cosmic cycle of birth, death, and rebirth? Imagine a universe that is constantly renewing itself, never truly having a start or an end. This is the intriguing concept behind the cyclical universe model, an alternative to the traditional Big Bang theory. It challenges our understanding of the cosmos and opens up new possibilities for how we perceive the universe. In the cyclical universe model, The Big Bang is not a singular event, but rather a recurring phenomenon. Each Big Bang marks the beginning of a new cycle, following the end of the previous one. Instead of a universe expanding forever, the cyclical model proposes that the expansion eventually slows down, stops, and reverses. This reversal is a crucial aspect of the cyclical nature of the universe. This contraction leads to a big crunch where the universe collapses back in on itself, only to bounce back out in another Big Bang, starting the cycle anew. It's a continuous loop of creation and destruction. This endless dance of expansion and contraction could potentially solve some of the puzzles that plague the Big Bang theory. It offers a different perspective on the mysteries of the universe. For example, the cyclical model offers an explanation for the remarkably uniform temperature of the cosmic microwave background radiation, suggesting that it's a leftover remnant from a previous cycle of the universe. This could help us understand the origins of the universe's uniformity. One of the most famous proponents of the cyclical universe model was the British physicist Sir Roger Penrose. His work has inspired many to reconsider the nature of the universe. Penrose proposed a model known as conformal cyclic cosmology, which suggests that each cycle of the universe leaves a subtle imprint on the next cycle, encoded in the cosmic microwave background radiation. These imprints could be the key to unlocking the secrets of the universe's past cycles. While the cyclical universe model faces its own challenges, it remains an intriguing possibility that captures the imagination and offers a glimpse into a universe that is not bound by a single beginning or end. It invites us to think beyond the conventional and explore the infinite possibilities of our cosmos.